Looks like that at the moment, you know. I managed to take a picture when I was on La Palma and I got M31 out of the Milky Way all in the same shot.
Yeah, you
Proper camera. It's no factory involved.
So, hi, welcome everybody. So we're going to start with the lunch talks, and you'll be pleased to know for at least this semester I won't be bugging you for talks because the entire schedule is full. Ching! So the first speaker of the year of the semester will be Indranil. He's a PhD student here. As you can see, the talk is being recorded. You're not in the frame, but if you talk, your voice will be, just so you know. So Indranil is going to talk about galaxies without dark matter.
Okay, so thank you everyone for coming. So I'm just going to be talking about trying to understand galaxies without adding dark matter to them, so just using their visual mass. And hopefully the significance of this picture will become clear as we go along. So just to recap, the one of the reasons for inventing this dark matter is that if you apply the Newtonian gravity, which works well in the solar system, to the visible mass distribution of galaxies, that you get a prediction for the acceleration. And that predicts like the rotation curve should do something like this. So for example, the outer planets in the solar system are rotating slower than the inner ones. But in galaxies, that doesn't seem to happen. So once you're beyond most of the visible mass by around here, the rotation curve remains flat. And this discrepancy with the prediction of Newtonian gravity is what this talk is going to be about. Now, one possibility is that it's caused by dark matter. So the idea would be galaxies look something like this, with this blue sort of halo of dark matter around the visible part. But there's no actual evidence for this. So this is what galaxies actually look like. There may be invisible mass here. There might not be. That's just a hypothesis. There is now to try and quantify this the discrepancy that we see. What's done on this slide is we're going to show the predicted acceleration applying Newtonian gravity to the visible mass, and on here we're going to show the ratio of the observed acceleration divided by the prediction. So in theory, everything will line up along this line at 1 if the Newtonian gravity works. Now we've just seen that's not going to happen. So what we're going to look at though is the exact way in which the discrepancies arise. So where do you get points above this line? If you get points like just randomly tiling this rectangle, then you need some dark matter. Because obviously in that case the visible mass can't be used to predict the dynamics. There's something going on that's different. However, if all the points are going to line up on a certain smooth line here, then you don't need the extra degree of freedom in the invisible mass. You just need to predict the acceleration, and that will tell you what the boost factor should be, and you'll be able to get the answer. So which of these two is actually correct in the real world? So this is how the data actually looks. So we get like maybe 10 points from one galaxy here, and then there's 100 galaxies. They all seem to very closely follow a particular relation, which means that you don't really need the dark matter. It's actually disfavored by the data, I would say. You just need to look up the acceleration. That tells you how much the boosting factor is, and that tells you the dynamics. Of course, the fact that it's not along this flat line means that you have to use a modified gravity law. Now, let's have a quick recap of how the Newtonian gravity works. So it works like this. The gravitational field equates with the centrifugal acceleration. Now, it doesn't always work, of course. So if you use this to calculate v and you got an answer close to c, which is the speed of light, you know this equation is not going to be very accurate. So you have to use other theories then. Now, that's for high speeds. What about with quantum mechanical effects? Like, does that affect this at all? Or more accurately, when does it cause a breakdown of that equation? So the Newtonian gravity I was showing you just now, and the general relativity that leads to it in the galaxies, It's a classical theory. It assumes you can get arbitrarily precise positions and velocities, even though that's not obviously possible. Still, you can assume it is, and what does that mean? So if you had a reasonably heavy mass here, you might get some space-time looking like that, and you approximate it like this. So of course, this is how it actually looks, because there's some quantum uncertainties. But this is the approximation. Of course, if you're going to apply the general relativity everywhere, then you also have to apply it in a situation like this, where the curvature is much less, the gravity is much weaker, and you'd approximate it like this. The only problem here is if all these wrinkles carried a reasonable amount of energy, then there'd be way more energy here than here, for example, and this isn't a particularly accurate approximation. This might be fine, but here it doesn't look very great. So you have to consider the quantum fluctuation somehow. We don't have any way to do that right now. But roughly speaking, this is the picture you can have in mind, that you look at space-time without worrying about the precision too much, and it kind of looks smooth. But if you kind of pay it down really closely and try and get things to the 10th decimal point, then things might start behaving a bit weirdly. It might be hard to get predictions that accurate. To try and quantify this, you can realize that empty space seems to have a minimum energy, the vacuum energy, which we know about because it's causing the universe to accelerate apart. Okay, so this is what's called the dark energy. At least this is the most logical interpretation, I think. And that is a minimum 0-point energy of the vacuum. In kind of a similar way, I suspect that a spring has a minimum energy quantum mechanically, or a pendulum has a minimum because it can't always be still at the bottom. Now, the important thing is, it's quite hard to calculate how much dark energy there should be. But you can measure it, and you can use that to estimate when quantum gravity effects might be important. So what you can do is equate this vacuum energy with the energy in a gravitational field. So these are energies like densities, I should say, per unit volume. And what you get is, of course, at sufficiently low G, you're going to have less energy in the gravitational field than in the vacuum. The transition is going to take place here. So the picture to have in mind is something like this. Maybe as you change the gravitational field strength, classically the energy density just does that. But we know that if there really wasn't anything at all, just pure vacuum, well, that still has some energy density. So basically in this range, we have got no real idea what should happen. So what that means is that unless the quantum gravity regime works exactly the same way as the classical one, the Newtonian gravity is probably not going to work. And the lower the acceleration, the more important these quantum effects, and therefore the bigger the discrepancy is probably going to be. So we don't know how to calculate this a priori. But what you would do though is look observationally for an acceleration-dependent discrepancy with the classical theory. So for regions where the gravity is weaker and weaker, the discrepancy is larger and larger in fractional terms. Obviously in absolute terms it's still getting smaller, one would hope. Yeah, that's a thing to be on the lookout for effectively. And you can see that that is indeed what's happened. More importantly, that why the data points have started drifting above the 1-to-1 line, it's close to the acceleration we just calculated. So the solar system is way over there, maybe 10 to 0 meters per second squared, something like that. When it's 10 to the minus 2, minus 4, minus 6, the data is all still on the 1-to-1 line. Suddenly around about here, where you'd expect quantum effects to kick in, that's roughly where the data starts to deviate from the Newtonian gravity prediction. So it does look like a quantum gravity effect is causing this discrepancy rather than anything else. So just to show you that if you try and plot this with distance on the x-axis, like distance from the galactic center where the data point is collected, then you get data, like points all over the place. So there is no clear correlation between this acceleration discrepancy and position within a galaxy. It is, however, correlated with the acceleration, with the gravitational field strength. This is how the data looks for about 150 spiral galaxies. They all follow very closely this relation. You can see that there's no real, you can't see 150 individual tracks on here. That is because all the different galaxies have lined up. So basically data points from the outer part of a like a bright galaxy, where the acceleration is low, line up at the same place as the inner part of a much fainter galaxy. They fall at exactly the same point on this relation. With the transition from the one-to-one line coming around where you'd expect from the quantum gravity effects, and the residuals follow this pattern, so like 0.1 dex, uncertainty either way, probably observational errors. This is where the idea of modifying gravity comes in. It just says that there's no need to do anything fancy on the previous slide. You just have to boost gravity by some factor, which you basically could have read off on the previous slide from the graph, like how much that factor should be. It's an empirical theory. The reason for that is because we don't know exactly how to do quantum gravity. And by the way, there are some recent proposals for how to derive one from like a deeper principle about quantum gravity. But I'm not going to go into that right now. Instead, we're going to try and look at the consequences of this modified gravity theory. So the basic thing to do is to say that the gravitational field times a mu function is equal to the Newtonian gravity. So this mu function is what modifies the gravity. It's 1 at high acceleration, so when mod g is much above the threshold, and x, mu is equal to its argument when gravitational field strength is much less than A naught. So you're going to, in that regime, you're going to get this. You get g squared over A naught on this side. So if you put in Gn being what it is for point mass, you'll get an inverse R relation. You'll get this. So the inverse R relation is what is required to fit flat galaxy rotation curves. That's not a prediction of mod as such. What is a prediction is the normalization. So if I just show you like that we're going to equate the gravity with the centripetal acceleration. So the V will be the fourth root of GMA naught. That means in the outer part of the galaxy, the rotation curve should nicely flatten at this level. So what happens in real galaxies, rotation curves do flatten. What we're going to show here is the V in the flat part against the mass, and the prediction of mod is this red line. At least it's aligned with that slope, is the prediction of mod. And the important thing is that the star-dominated galaxies have lined up along it, but the gas-dominated ones have lined up as well. It's interesting because if you plot the star-dominated ones and just the stellar mass of the other galaxies, then you get things to deviate from the relation, and then you think like, oh, this modified gravity doesn't really work. But then you add in the mass of gas in these galaxies, and then it does work, all the way down to very low masses. Like, so you've got about a factor of 100,000 in mass on this graph. In classical gravity, it's quite hard to understand how this happens. Because what should happen, galaxies first of all should follow this dashed line, which is to do with the baryon to dark matter ratio being the same as the cosmic value. At least the galaxies should have started on this line initially. The current thinking is that they've lost a vast fraction of their baryons. So they've gone down. The V hasn't changed because most of the mass is dark matter. But they've lost most of the visible mass. This is caused by various processes, which are not all unknown. Things like supernovae, for example. But the important thing is that the process is random to some extent. I mean, it's quite messy how this would work. It can't always work the same way, surely. It depends on the environment, the star formation history, things like that. So obviously the light and dark blue points have different star formation histories. So a tight correlation of how much baryons you've lost with the baryonic mass is unlikely, right? So you should have much more scatter about this relation. Because some galaxies should have lost 90% of the baryons, some 95%, something like that. But that doesn't really seem to happen. Now, that's just the outer part of the rotation curve. If you look at the rest of it in detail, you get some interesting cases like this, where the rotation curve is with the data points. The Mond prediction seems to have worked well. The Newtonian prediction is way down here. Importantly, how do you want to solve this discrepancy? You can either solve it by adding dark matter, but the dark matter is like collisionless and smooth. It forms a smooth halo. So you're going to end up with a nice blue curve like this, like a smooth dark matter halo, which will boost the rotation curve. Or you can multiply Newtonian predictions by some factor, which is going to be larger at the lower acceleration outer regions. If you do the second option, then this dip is going to stay there. So you're going to have a rotation curve which doesn't look smooth but has a dip here. So then the only question then is like, yeah?
Well, I was just, if you just added the gravitational contribution from the baryons to the dark matter, wouldn't you get basically a similar thing?
Yeah, but the dip would be much reduced because they're added in quadrature effectively on a graph like this. Yeah, so this is how it. Most of the mass would be dark, right, and smooth. So that would be the issue. Yeah, I guess like if you try to do this more accurately, you'd get a small dip in the blue curve, but not very much. So this is essentially like the NGC 1560 or the more well-known case. There's other cases like this. This is called Renzo's rule, that there always seems to be a dip where there shouldn't be. And the dip would be there in Newtonian gravity as well, but like much smaller. You'd hardly be able to see it in that theory. One thing to look at is some of the dwarf galaxies, which should be dominated by dark matter in the classical picture, like the one I was showing on the previous slide actually. Now we can do the dark matter only simulations, and you can just predict the rotation curve. It can't be modified much with baryons because they make up such a tiny fraction of the mass. So even if they all exploded, it wouldn't affect the rotation curve much. What happens in these galaxies? So this was a paper by Oman from 2015, and showing like the Newtonian predictions for like 4 galaxies and the observations. So the range here is the range of uncertainty because of not knowing what happens to the baryons. The baryon physics is hard to monitor, it's not that important in these galaxies. And you can see it doesn't work here. So let's see what happens with Mond in that example. Remember, Mond only had one free parameter for all galaxies. So in this case, Mond's managed to work okay. So in this case, it's fit reasonably well. This one, kind of. This one, small normalization errors like this might imply the inclination is not being got exactly right. But the general shape has still been matched across like quite a vast range of rotation curve amplitudes and galaxy masses. This is an experiment people did in 1998 where you give astronomers like a rotation curve and an image of a galaxy, and you get them to try and fit like the rotation curve based on the photometry. So what happened in Mond is that it really couldn't be made to work. But in the Newtonian gravity and dark matter, they got a very good fit actually. This series like worked much better for this galaxy. Except this wasn't a real galaxy. What had happened is people had like given people the astronomers like a rotation curve and an image of a different galaxy to fit, just to see if they're going to be able to fit it anyway, or if they're going to fail. And in one people failed, with the Newtonian gravity they fit it anyway. because the theory has a lot more flexibility. Now, the mass to light ratio, you can ask like if that's reasonable, because what you're doing in these Mond rotation curve fits is adjusting that until it kind of fits. You shouldn't be able to do that too much. I mean, you can kind of estimate what the mass to light ratio should be based on the color. And we're going to just see on the next slide like what happened. So the mass to light ratios required by Mond are shown as these points. And the kind of expectation based on our understanding of stars is that the mass to light ratio should slope upwards depending on the color in the blue band, in this case in the infrared here. And there should be some amount of scatter because of things like different metallicities. So what happened in both photometric bands, like Mond has got like the slope, right, and the normalization, and the scatter about it even is kind of right. So the mass to light ratios that we require in Mond, although we adjust them between galaxies to fit the data, they are reasonable given our understanding of what the mass to light ratios should actually be. In the elliptical galaxies, it actually, they follow like the same radial acceleration relation thing as in spirals. So the observed gravity and the ratio of the visible mass in Newtonian gravity, like they follow the same relation as well. So that's quite interesting. So now we've seen some interesting correlation outside the local group. Maybe if we look inside it, we'll be able to do things a bit more accurately and try and see which one is actually correct. So the local group, roughly speaking, it looks kind of like this, with a small number of satellites. In a dark matter simulation, it looks like this, which is quite weird. So most of the satellite galaxies in here must have just stayed dark and not formed stars. But I'm not going to be focusing on that in this talk. Instead, what I'm going to be focusing on is that these are distributed more or less spherically symmetrically around the host. So how does that compare with observations? I mean, so in the Milky Way, for example, you've got like the disk here and a plane of satellites here. By the way, like it's only these gray zones that are unobservable. If there had been satellites here, we should be able to see it. I mean, the Magellan Cloud, for example, is discovered 500 years ago. So, yeah. So the thing that's happened here is the Milky Way satellites are rotating within the plane as well. So it is quite anisotropic. Now, just to introduce some things we'll do later, this is an actual image of an external galaxy with a disk, and like something happened here. Another galaxy kind of spiraled in and merged with it. And maybe if this had coalesced into like a large number of satellite galaxies, there would be a plane of satellites around here. So that leads to this formation scenario where two galaxies interact and they create a tidal tail. It's hard to show, but basically this tidal tail is entirely within like the plane of the board. So it's kind of quite anisotropic. And there's some real examples where this kind of thing has happened. Between some galaxy interactions here, and you form like a tidal tail with galaxies forming where they've been labeled. And here as well, there's some tidal dwarf galaxies forming where they're not so particularly dense. So we can kind of get it to work in simulations as well. But it's a bit controversial, so we'll try other explanations for the satellite planes first. What's shown here is the probability density of getting different amounts of angular dispersion on the sky from the satellite planes. Like if you get 0, then they're all exactly in the same plane. And the isotropic distribution is the thin like line. The first 8 simulations are like standard cold dark matter models. Here you've got like a flyby of a galaxy as heavy as the Milky Way past us, and these are mergers. You can see the last 4 models work okay. So we're going to be looking at scenarios where another galaxy like interacted with the Milky Way, and would that explain the observations? So first of all, with Andromeda, you have much the same issue. That you also have 15 galaxies in a thin plane around it. The ones above are going away from us, these are coming towards us. So it's like rotating. Unfortunately, we happen to be more or less in the plane of Andromeda satellites. So that's interesting. Now, maybe that ties in with the flyby scenario I was describing, where these galaxies flew past each other. But let's just have a quick look at this. So side on, it looks like this, and if you do a calculation, like you can see that in order to get 13 out of those 15 to be rotating in the same sense, that alone is very unlikely. Only 0.7% of the cases that will happen if it's isotropic, let alone getting a plane back in the first place, which is obviously quite unlikely. So if you look at it in sort of the lambda CDM simulations, you want a co-rotating system, so 13 out of 15 co-rotating. It needs to be thinner and wider than observed. So it needs to be thinner than observed and wider than observed. It needs to be in this red box. Now, you can get like thousands of Andromeda analogs in a cosmological simulation and like see if any of them satisfy all these criteria. And the reality is like about 3 did out of like 8,000. So it's very unlikely. But it happened around the Milky Way as well. So you have to square the probability. So this seems very unlikely. And one of the scenarios people think is that galaxies form where these dark matter filaments intersect. But you can see that the M31, the Andromeda satellite plane thickness is like much thinner than cosmological filaments. This is actually like the correct scale of the thickness. It is as thick as that line. That's one problem. The other problem is that if galaxies are falling in along this filament, then they'll be on very radial orbits. The Milky Way satellites are mostly on circular orbits around the Milky Way. So that's the problem. For the Milky Way, for Andromeda, we don't know things in that much detail.
Sorry, Neil,
Yeah.
that's like, what's that ring there?
That's just like showing the virial radius, I think.
Okay, and that's the blue line, white line is the disk of satellites.
The radial extent is like, it's not actually that long, but I've got the thickness to be the right.
If you had two galaxies in there, one for M31 and one for the Milky Way, wouldn't you then change the way this simulation works?
People have looked at these things, like if you have, people have found like lots of pairs of galaxies. Like there's a paper by Pawlowski about like having a Milky Way analog and an Android analog like a megaparsec away. It doesn't change change the result. You still don't really get anisotropic satellites.
That's like having one at the top of or bottom
Well,
of the
I think
star.
it would be like having one somewhere around here maybe.
No,
it looks like
it should be 700 kiloparsec, 800 kiloparsec away.
Yeah,
Okay.
I think this is about 800
Okay,
kiloparsec.
I see.
But yeah, people have looked at it. It doesn't seem to affect the results very much. If we include the so far we've talked only about the dark matter basically. If we include the baryonic effects, you might have more luck. And the reason is that the dark matter can't radiate and cool and form these thin disks in under any circumstance. So a plane of satellites is just one example where you couldn't form a disk anywhere. The baryons, however, can settle into a disk, and maybe that's what happened. If we pull lots of baryons out of Andromeda and then use the dissipation to form a thin disk, or the fact that they're already in a thin disk to begin with, if we use these, could we get to match the observations? Now, obviously you can't just have a rotating disk like randomly shoot material out of itself. So what would have happened is there must be another galaxy interacting with it. But that's not a problem for the scenario. What would happen is you would get an anisotropic like distribution of tidal debris, a dense tidal tail, and like lots of tidal dwarf galaxies. Now the problem, the thing with that is that the dark matter is dynamically hot, as we say, so it's like a hot gas surrounding a galaxy. If you try and just pull on it with another galaxy, then it will just disperse very rapidly and the density will be extremely low. It wouldn't collapse into galaxies. So the dark matter will not end up in the tidal dwarf galaxies. So this tail, for example, is only going to be baryons. There can't be lots of dark matter like following the same distribution. That wouldn't make any sense. Now, if you look at so you get some things to work. Now the satellites also can't accrete dark matter later because the dark matter's typical velocity is say like 100, 200 kilometers a sec, whereas these satellites have escape velocity maybe 10 kilometers a sec. So they can't accrete dark matter from the Milky Way. They're not born with it, so they'll simply be free of the dark matter. But otherwise there's no problem with the scenario. Now then we need to look at the internal dynamics of these satellites, and you see straight away that the mass to light ratios interpreted in Newtonian context are very large for some of the fainter objects. So that looks a priori like Newtonian gravity doesn't work for these objects at all. So maybe it's caused by tides from the Milky Way, like disrupting these objects. So to test that, people looked at the issue of tides by dividing the size of each galaxy by the tidal radius, beyond which it would start to disrupt. And basically these galaxies are all like maybe 1/10 as big as the tidal radius. So the tides shouldn't really matter. Also there's no correlation with how much tides should affect them and like how far off they are from the prediction of Newtonian gravity, which is this black line. So they shouldn't be affected by tides, and the observations suggest they're not. Now in MOND, we're able to get a lot closer to the observation. We still struggle at the lower mass end, but of course we need to redo the tidal calculations to see if tides can explain these. I mean, sort of work a bit differently. So in this case, what's happened, a lot of the galaxies around here actually work in MOND, as we saw in Newtonian gravity. These ones still seem to fall apart. MOND doesn't work very well in them either. But they're quite large compared to the tidal radius. So maybe they are actually being disrupted by tides. I mean, you could argue these are being disrupted. You can see a correlation here. So here it looks like it's just with tides. The objects that are least affected by tides, where you think like, well, one should really have worked there. Well, there it does actually seem to work. Yeah, well, another thing that people have looked at is the issue of binary stars, whether that can inflate the velocity dispersion of these galaxies. And the way to do that is you calibrate it, the parameters of the binary star population to get one here, so the observed by the model prediction. You adjust the model until you get one here, and the reason is that at the very low mass end, basically all the velocity dispersion would come from binary stars actually. The intrinsic one is going to be so tiny. So you're going to get one here, at the high mass end, both theories seem to kind of work, so you get one there. At the intermediate scales, MOND has worked okay, but the Newtonian gravity gets velocity dispersion maybe twice as big as what they're actually observed to be. So it looks like even with binary stars, you can't really understand what is going on with these galaxies in a Newtonian gravity context. What we've just seen is that the satellites do actually seem to need dark matter to explain. You can't just use the visible mass in a Newtonian gravity context. Now, but they can't have dark matter though, because otherwise how did they end up in a thin plane? The conclusion then is that you can't have Newtonian gravity actually working in these objects. Their high internal velocity dispersions must be caused by something else. In Newtonian gravity, just to remind you, the Milky Way and Andromeda like separation kind of works like this. So there's never any close flyby between them. In MOND, if you integrate the trajectory back, because of the much stronger gravity and because they're on a nearly radial orbit, they end up having a pass-close flyby. So what you need to do is adjust their masses a little, so that they kind of, so for example in the red trajectory the mass is too low, so they get close to the Big Bang still widely separated, and then suddenly they have to drop to zero at the Big Bang. So that means they're not on the Hubble flow at early times. They're not following the uniform expansion of the universe at early times. They need to get together really quickly. In a way that's not physical, because if you think about it forwards in time, we know the universe is very homogeneous early on. At these times gravity hasn't had time to act very much. So the Milky Way and Andromeda should be following what's called the Hubble flow. So the red trajectory doesn't work. But then you think, if we raise the mass a bit, will it work? So you get the black trajectory, and that works. But if you raise it too much, you get the blue one, and then the galaxies basically are at the same point after the Big Bang, and then maybe they would have bounced here. But you can kind of tell that trajectory is wrong as well. So yeah, this is what's called the timing argument, and in modern it can be made to work with basically just the visible mass, we'll show later. Yeah, this is kind of the best fitting trajectory for the galaxies. Now, if we look at the disks of the two, what we did, that may be a good idea too. Okay, so what I'll do quickly is show you like a movie of how the Milky Way and Andromeda interacting might have looked like. It'll kind of, they essentially something like this. They get a bit disrupted, and we're going to use some careful statistical tools to look at what just happened. But that's the basic idea. Something like this. Okay, so some flyby around that in terms of time. With like a 50 kiloparsec maximum separation. It couldn't be much closer than that, but something around that at the most. So what we did to investigate this is we set up like test particle disks around the Milky Way and Andromeda, which we took using point masses. So solving even the gravity of 2 point masses is quite difficult in one. We did that, and we got the gravity of the Milky Way and Andromeda to act on those test particle disks. The galaxies themselves follow the trajectory we just looked at. Then you get the final spin vectors of the disk remnant, so the central regions of the disks, which stay more or less undisturbed, but they precess a bit. So you tell the initial disk orientations, so the final ones match the observed values. I use like 2D Newton-Raphson method, but the disks are independent because it's just a test particle simulation. So you can fix the Milky Way and then fix Andromeda. You repeat it like for different model parameters. So the main model parameters here are the orientation of the Milky Way Andromeda orbital plane. So if you see Andromeda like in that direction, then the orbital plane can be like this, or it can be like this. So we need to rotate that. You could adjust the close approach distance a bit, as long as it's below the upper limit. You adjust like the external gravitational field on the local group, because that affects forces in one. It's a nonlinear theory. But the time interval of this external field is constrained, because you can see how much the local group is moving with respect to the cosmic background radiation. You can adjust the exact history, but the time interval could be adjusted. So there's not much room to adjust it. There is a little. So here we show like the large-scale geometry of the problem. In the galactic coordinates, so if a galaxy is if the objects are moving around within this blue plane in this sense, then the angular momentum is pointing vertically up. So that's just the usual right angle for angular momentum. Now the Milky Way disk is at this point, and the Andromeda disk is over there. So that's just orientation of the disk that we see. For the Milky Way,
the angular momentum.
Yeah, the angular momentum.
Yeah,
so the Milky Way satellite plane, the angular momentum of that is pointing in this direction, around there. For Andromeda, it's around here. What we think happened, of course, is that the material in the Milky Way has been tidally torqued to go from all the way down there to up there. This is what a simulation has to get for it to be right. For Andromeda, it needs to have gone a smaller distance, but the Milky Way is less massive than Andromeda, so maybe that makes some sense. The actual Milky Way Andromeda orbital pole is constrained along this orange arc at like 1 sigma, but at 2 sigma, anything all the way around the great circle is possible. So all orbital pole directions are feasible as long as they're orthogonal to the Milky Way Andromeda line, obviously. So we don't have too much constraints on this orbital pole, so we can try different values. So this is the kind of basic thing that happens in some of our models. you get the Milky Way, is shown in the top panel, Andromeda in the bottom. So the Milky Way material starts at minus 90 degrees, so at the south galactic pole, and it ends up where it's shown here. You want it to end up close to there. For Andromeda, the disk is spinning here initially, and you want it to end up there. So what these plots show is the angular momentum distribution of the tidal debris around each galaxy. So you reject their disks and show all the material around them and plot out their angular momentum directions. This model hasn't worked that well, but we'll just show you some other models. So if we vary the, so this shows like a 2D grid, like a low resolution. So up here what's happened is we're changing the geometry of the problem, keeping the closed approach distance similar. But if you change the geometry, you can see the Milky Way material has more or less stayed at this particular longitude, whereas in this simulation it's at a very different longitude. So that obviously changes the geometry of the satellite plane. If you go this way instead, you have a much weaker encounter. So for example, if you look at Andromeda, the disk has been disrupted, and the material ends up with quite different angular momentum to where it started. Whereas in here, the material ends up close to where it started in angular momentum space. That's because obviously there's less tidal torque in this model. Right? The galaxies have roughly a 3 times more distant encounter. So that's kind of what we did. Is we tried a grid of parameters.
So in the extreme case of two things fly by widely apart, how do they look like?
Flying by widely, the Milky Way will stay as a red line at minus 90, and Andromeda will stay exactly at this blue dot. So nothing will happen really. So this is kind of our best fitting model. We managed to get more or less the Andromeda disk to precess to the tidal debris to line up with its angular momentum. So essentially we've got debris spinning around Andromeda in the same way as its satellite plane. For the Milky Way, we've kind of got material spinning around in the same way as its satellite plane. So these models don't have hydrodynamics. So in the real world, probably if you had a reasonably thick plane, it would have thinned by dissipation, and you would have settled into somewhere close to here, because the average angular momentum would still be conserved. It's just there would be less dispersion about it. So you can imagine this model has probably worked. We looked at the thick disk of the Milky Way as well. So the Milky Way structure, just to recap, looks like this. There's a thin disk, a thick disk, and a halo around it. Now the thick disk has, first of all, you could get some amount of disk heating because of stars interacting with each other, but you can only get up to about 25 kilometers a second vertical velocity dispersion out of the Milky Way disk, which is not very much. So if people looked at the actual velocity dispersion, one thing is the bottom panel, the vertical one, and as you get older and older, for stars which are older and older, the velocity dispersion stays at this 20 or so. It's saturated. But here, at about 10 billion years ago, there's a sudden jump. The stars older than that have a much higher velocity dispersion, which these authors took to mean that there's probably an interaction with another galaxy about that time. So recently we've looked at it and found that this shock thing is more significant at larger radii. It's characteristic of tides as well. Now what those authors said is, based on the Hipparcos data, is that stars older than 9 plus minus 1 giga have a much higher velocity dispersion, and that is probably formed by a minor merger. Or in one case we think it's a major galaxy flying past, but it will be something like that. So we managed to match the vertical, we didn't look at the velocity dispersion, we looked at the actual height of the thick disk. The velocity dispersion will be sensitive to the gravity exerted by the disk, which we don't directly include in our model. But what we did get is, so the observed thickness we got from here, that corresponds to measuring stars between 3 and 5 disk scale lengths, because the sun's at 4, so they looked in a narrow range about it. We managed to get that to work, but only for a narrow range of impact parameters. So basically we can't choose the closest approach distance arbitrarily, it's kind of fixed by this. And then if that model doesn't work with the satellite planes, then we're in trouble. These are kind of some of the numbers we get out of the model. A reasonable local group mass, the baryons definitely is at least 230 billion, but probably another 30 or 14 hot gas halos. So it's reasonable. The flyby time is reasonable. It's supposed to be 9 GeV ergo plus or minus 1. We got the thick disk height more or less, right? And the satellite planes to be about as wide as they're observed, with about 1% of the disk mass ending up in the satellite plane. We didn't get any counter-rotating material for Andromeda. We got some for the Milky Way. So things rotating in the opposite sense in the same plane, which is good because there's no observed, that clear evidence of counter-rotators. Whereas in the Milky Way, we know that Sculptor is counter-rotating within the orbital plane of the remaining satellites. That's just to show you what the Milky Way satellite looks like, and the Sculptor you can see is like a counter-rotating. And the radial extent is about 150 kiloparsec here. For Andromeda, it's like similar. Also like 150 kiloparsec radial extent that we got similar to observations. To summarize what we've been doing, you could see some galaxies within tidal tails, what are called tidal dwarf galaxies. Nearby satellite galaxies also lie within thin planes, but it's hard to form them any other way than by tidal dwarf, as tidal dwarfs. So these galaxies will probably form like that. It is hard to see how else it could work. But in that case, they should only contain baryons, because the dark matter can't cool and form these dense tidal tails. We can't form disks ultimately. However, using just the visible mass of these galaxies, the velocity dispersion is predicted to be much smaller than observed. So the actual high velocity dispersions we see indicates a rather strong self-gravity, which can't be explained by dark matter. So it has to be explained really by modifying the Newtonian gravity. That's essentially the introduction. We're going through how Newtonian gravity needs to be boosted in galaxies at low accelerations, where the classical gravity might fail. Now, if that is actually right, then you could do the modified Newtonian dynamics, which doesn't just predict this, but it predicts other things as well, like an ancient flyby of Andromeda past our galaxy, which might explain the satellite galaxies in thin planes. It could explain the internal dynamics, the high velocity dispersions. What we found this summer is that also it can explain the orientations of these planes. It can explain the large-scale geometry of the satellite planes. So hopefully we're looking to do more detailed, like hydrodynamical models with the Phantom of Ramsey that can handle a lot more physics than our simpler models. Okay, so thanks for listening.
We have time for some questions. Andrew?
Just thinking back to your early slides where you looked at the curve as a function of acceleration.
Yeah.
And thinking about your discussion of the quantum fluctuations,
Yeah.
can you actually use that the shape of that distribution and its amplitude as a function of acceleration to deduce something about the spectrum fluctuations?
Potentially. I mean, all that actually happens. So the only thing that's clear-cut by now is that the slope has to be like a half here in logarithmic terms and 1 here. The precise interpolation you could do, like people have recently found one particular way of fitting things works better. It can't be much more gradual or much sharper. Yeah, potentially. I don't work on that kind of thing, but it is possible that you can, or you can do it the other way around as well. You can predict what the interpolation function should be from a quantum theory.
Yeah, you can either work the forward problem and remodel comparison, or you can try direct inference.
Yeah.
Yeah, just
That's a good question. So maybe
Yeah.
you know the volume density of galaxies, at least big galaxies, and you can aim for, say somewhere like something like a twice solar distance. Okay, some 18 kiloparsec-ish from a center.
That would be quite
And then the typical gravity is there, and you sample all galaxies at this gravity, and you maybe build up the statistics. of the volume vector of the universe that's in this gravity fluctuation.
And, that's an interesting thought actually, to try to constrain the quantum gravity. That's what I'm hoping happens in the long run, that people use the empirical wand theory to try to understand the underlying physics behind it.
In the universe, we see quite a lot of galaxies that are in a coalescent stage of merging, or which have already coalesced. What's special about the sort of Andromeda Milky Way initial conditions in that they take 20 billion years or so to do what other galaxies take 2 or 3 billion
I mean, it's going to vary depending on the environment, right? With the Milky Way and Andromeda, they must simply have, if they started closer together, they'd have done more close passages by now, for example. If they'd been farther away, they might never have had one. I don't think it's particularly special because the local group is relatively underdense. So it's quite hard for anything else to put much tidal torque on it. Therefore, if you were to form 2 large structures in it, chances are they're going to be on a close to radial orbit. And if the separation is in a reasonable range of values, there's going to be one interaction between them. So I think I don't think it's particularly special.
Yeah, so...
No problem. I'm sorry.
That's fine. So I mean, I guess measuring merger rates and merger histories and stuff for galaxies is pretty difficult. But I guess cosmological hydrocodes do a reasonable job at measuring these things, and they produce galaxies that are reasonably similar to in our universe. So if you have this one scenario, then wouldn't this quite drastically affect the merger rates? And
it would affect the merger rate, but you're not right about the it matching so well. I mean, the large fraction of the bulgeless disk galaxies, for example, argues that interactions between galaxies are actually quite rare. Otherwise, because usually what seems to happen in these simulations is very hard to get galaxies which are pure disks without a bulge. But yeah, regardless of which way the evidence points, there is something to be done here about the merger fractions. The only problem is that you could either have one theory like the lambda CDM, where mergers are relatively quick but common, or in MOND where they're rarer but they'll be visible for much longer because they wouldn't merge efficiently. So there's a degeneracy between the merger frequency and its visibility effectively.
Last question, please.
If I understood your simulations correctly, you're predicting that the satellite plane in Andromeda is much thinner than that for the Milky Way.
That is observed.
That was my question.
Yes.
Is that effective observed?
Yes. Assuming the baryonic dissipation preserves some of the features we see, it's likely Andromeda's plane would end up thinner, and it is thinner. It's about 13 kiloparsec. The Milky Way one is about 20. The Milky Way one you can see is much more dispersed on the sky as well in terms of the orbital angular momentum directions compared to Andromeda, which seems to be a very thin plane. And there is some evidence for this.
Okay, thanks for a great talk, and let's thank you again.